All right, scholars, welcome back to our continuation after the first leg of our journey through polynomial sketching. To date, we have become well versed in this idea of what a factor is with polynomial division, the end behavior, the multiplicity of a function, the difference between standard and factored form, the end behavior, the leading term, the degree of the polynomial. So we are going to veer deeper into the polynomial space. It's not really a polynomial anymore, and venture into rational functions and how we can transition some of those key concepts and terms um, to the applicability here with rational functions. So we're going to identify vertical and horizontal asymptotes of simple rational functions from their equations so I can interpret a graph of a rational function and explain the meaning of the vertical and horizontal asymptote in context. I'll know I've got it when I can identify a vertical or horizontal asymptote from a graph or an equation of a rational function. All right, in our first screen, we are presented with a graph that we may not be normally accustomed to seeing. So I would like for you to take a moment to write down two things that you notice about this function and two things that you wonder. Saying that you notice that they are curved, yes, that is apparent. Try to establish some connection between the algebraic equations written and the graphical representation. What is the correlation between the two? All right, now we're going to start the tour de precalculus. I hope you laughed. Kieran's aunt plans to bike 10 miles. How long will it take her if she bikes at an average rate of 8 miles per hour? This might jog some of your physics memories, but remember, if we want to calculate time, time is equivalent to the distance. So the distance that Kieran's aunt will be traveling is 10 divided by the rate, in this case 8. So it'll take her roughly 1.25 hours to bike 10 miles. Now, knowing that that is the numerical equivalent for an average rate of 8 miles an hour, what does that expression look like if she were to bike at an average rate of R miles per hour? And then I would like for you to rewrite your expression, in this case for the average rate, um, if you are informed about how long you have to exercise. Oops, I think I went one too far. There we go. Now it's Kieran's turn. Kieran plans to bike 10 miles, so write an equation that gives his time t in hours as a function of his rate r in miles per hours, and graph your function. This should look strikingly similar to what Kieran's aunt had been doing. All right, and then you will graph a function accordingly. If you are struggling to picture what type of graph your function will create, I suggest obtaining a separate sheet of paper and making a table of values and plotting the corresponding points. I've decided to divvy up the axis by 2's. After you establish the function that you've created, determine what the meaning of t of 8 and the meaning of t of 0 is. What is the numerical output for those particular inputs, and what does that mean in this particular context? If you successfully graphed your function, you should notice something peculiar as r or our rate gets closer and closer to 0, and vice versa as r gets larger and larger. So please go back and reference your graph to assist you with those two questions. But if your graph in the previous activity does not resemble a graph of this type of shape, I would definitely go back and revise your thinking. But we're going to focus on publishing a paperback. So we have this function C here that represents the average cost per book in dollars when using an online store to print copies of a self-published paperback book. What is the approximate cost per book when 50 books are printed, 100 books are printed? So we can obviously do this in two manners. We have a function here that'll give us the most precise value, but we also have our graphical representation here that we can uh, drag and slide across so we can identify those corresponding outputs. Either one will be sufficient. because I'd like for you to consider if the author plans to charge $8 per book, about how many should be printed in order for her to make a profit. Once again, we can look at this graphically or we can look at this algebraically, but by the end of our journey, we will be able to look at them interchangeably. So taking a closer look at the end behavior here, right? So end behavior, if you've forgotten, is the really, really large values of x. So we're talking about these values here, right, as we're increasing and they're going off of the graph, right? If I could just continue going on to the right. What does it say about this particular context? From what I'm noticing is I'm seeing some type of horizontal behavior starting to unfold. And if I bring you back to our vocabulary words, we have this idea of a horizontal asymptote. An asymptote is basically an invisible line. If you wanted something familiar to relate it to, but it's a behavior that a rational function will exhibit over an extended period of time or extremely large values of x. Um, so taking a look at our function c of x, how can we rewrite this? Because currently it's pretty difficult if we substitute in really large values of x to algebraically determine what the end behavior is. If you've forgotten, when we have a single term in the denominator, that value acts as a common denominator. So we can actually tease apart the numerator like so. In the second term, 4x divided by x, the x's will simplify to a value of 1. So our original expression is really this, right? 120 divided by x plus 4. And if I were to substitute really large values of x into this rewritten function, you should know or recognize that the first term will become strikingly so tiny, we can assume it to be behaving like a 0. So then we define horizontal asymptote to be the remaining constant value of y equals 4, which means that if I printed 1 million books, it would wind up costing me around $4. However, it doesn't matter how large my value becomes, the amount I would ultimately wind up having to pay, base value, is $4. Try 10 million, 100 million, 1 billion, and I guarantee you that the value will never drop below $4 per book. So to conclude this activity, and since we've just started this rational function exploration, you're going to be matching up your graphs with the corresponding algebraic expressions, trying to hone in on what you notice in the denominator, because you should remember from our Unit 2 exploration, right? Those values in the denominator are what make the function undefined. So you should be able to notice some similarities between the algebraic representation and our graphical representations, and vice versa with our card sort, our second card sort. In this card sort, for each graph is going to have two expressions attached to it. It is up to you to decide which two those are. Right, and that's where we're going to pause. This lesson's a bit front-loaded. Okay, so the lessons toward the back end of this unit, only take us about a week, are much more scaled down. So gotta really dig deep here, settle in, and we will make our adjustments during our class time together.